Hello everyone, it's Mr. MathWell here. This video is a review for Chapter 1 in Math Makes Sense 9, so 9th grade, grade 9 math. We are reviewing Chapter 1. Now I'm assuming that you've gone through the lessons and spent some significant time learning this stuff. Today I'm just going to try and go over a quick video of the whole chapter, but give you the highlights and just go over some very important things. So we're going to talk about square roots of perfect squares and non-perfect squares. We're also going to talk about surface areas of different kinds of objects. All right, so square roots and surface area 1.1, we're talking about square roots of perfect squares. So what is a perfect square? Well, I was thinking about this, and you should have an idea of what a perfect square is, but if you think of just a square, right, that is a perfect square. Now, if I were to add one more square on beside here, would this new larger object be a perfect square? No, it wouldn't. And so I would have to add a couple more. Oh, pardon my drawing, this is all freehand. I'd have to add a couple more here to make this a perfect square. So that's another perfect square. And if I wanted to do that again, I would have to do something like this, right? I would have to keep adding more, and you kind of get in the picture here. That's another perfect square. So what did I do? Well, I had one square. That was my first perfect square, and it was a 1 by 1, right? So 1 squared is 1. The area is 1. And then I added 3 more to make 4. So here we have 4. And that's actually a 2 by 2 square. You see that? So that's 2 squared. And that is 4 squares altogether. 1, 2, 3, 4. And so on. So if you keep adding, if you think about it as a diagram, if you keep adding squares until you have a larger perfect square, that's how you build your perfect square numbers. So 3 squared is 9. You see we have 9 squares here. And of course 4 squared would be 16, and 5 squared 25, and so on. So these are your perfect square numbers over here. And the side lengths, so in this case, so this one that I have, there's a side length of 1, 2, 3 units by 1, 2, 3 units. They have to be identical to be a perfect square. Makes sense. Length equals width. And it just so happens that if you have 9 squares making up one larger perfect square, the square root is the side length. So the square root of 9 is 3. And my program totally just crashed on me. We're having some internet problems here right now, so if that happens again, I completely apologize. The square root of 16 is what? 4. The square root of 25 is 5, and so on. So here's another look at squares. So obviously there's 100 little squares in this one. So this is a 10 by 10. It's a perfect square. 100 units squared. So this would be, the area would be 100 square units here. And this one over here, if you think about this as 1 unit, and each of these tenths, you could go 1 times 1 is 1 unit squared. Anyways, I just want to get the picture of perfect squares. Now, it gets a little tricky when you're talking about fractions like this. Look at this weird fraction, 169 over 100. So the question is that a perfect square? If you didn't have a diagram, you don't want to make 169 little identical squares. But just to visualize this, I want to show you this diagram over here. So I have highlighted in blue, I have 100 of these little squares. That's 10 by 10. That's a perfect square, right? 10 by 10. Or 100 100ths, right? The blue is 100 100ths, okay? Now, if I added more little squares in such a way as to try to build a larger big square, if I could do it using 169 of these little 100th units to make a larger square, that's perfect, then this would be a perfect square number. And I hope you see, and I'll just maybe highlight this here, but you see all these extra squares that I've added onto the 100 squares, all those extra squares, now they all add up to 169. And so this is, as you can see, this is, right here is 13 by 13, right? Okay. So 13 times 13 is 169. So 169 little hundredths blocks is a perfect square. And the square root of 169 over 100 is simply, watch this, the square root of the top over the square root of the bottom. You just take the square root of the top and the bottom. So 169 over 100, the square root is 13 over 10. Okay? Let's practice that a little bit more here with this chart. Obviously, the square root of 49, you know, is 7. The square root of 64 is 8. The square root of 121 is 11, and 144 is 12. Now, you should memorize these up to 20, okay? Do your best. By the time you get into grade, 10, 11, 12, you should have those memorized up to 20 and make your math a lot easier. Everything will go a lot quicker. So start to memorize them now if you can. But look at this one, 49 over 100, and maybe I'll zoom in for you there so you can see that. But 49 over 100, well, Is 49 a perfect square? You bet it is. Is 100 a perfect square? Absolutely. So guess what? The square root is 7 over 10. Nice, eh? Look at the square root of 64 over 100. What's that? Well, that's 8 over 10, and so on. Okay? So the square roots, that's how you do it. All right, here's some more practice. Is each fraction a perfect square? Explain your reasoning. Okay. Now, I want to... Okay, so this one right here, 8 over 18. Notice that 8's not a perfect square, 18's not a perfect square. So you might say no and move on. Yeah, you got to be careful. You want to reduce the fraction as much as you can first, please. Reduce it, and I'll show you why in a second. Because 8 over 18 actually reduces, if you divide each of these by 2, it reduces to 4 over 9, and you should recognize 4 and 9 as being perfect squares. So actually, when you reduce something, you're not actually changing it, you're just simplifying it, okay? And so really, this is 4 over 9 in disguise. So this is a perfect square. It is. Now, pictorially, it's a little bit different to understand, I would say. But if we have 18 identical squares, you can't arrange them in a perfect square. But you can arrange them in 2 identical perfect squares. And if you have 4 blocks shaded in out of the half of the 18, which is the 9, then 4 out of 9, that's a perfect square in a perfect square, you're good to go, okay? So think about it that way. Reduce your fraction first. Let's see, look at B. Okay, we can't reduce the fraction. This is a perfect square. That's not. So this is not a perfect square. 2 over 9 is already reduced. 9 is a perfect square. 2 is not. So this is not a perfect square. Okay, and I just kind of drew 2 over 9 over here. Sorry if you can see that. I'll get my face out of the way. 2 over 9. So obviously, if you have ninths, if you have 9 squares, you can't make 2 of them into a square. It's a rectangle. Okay, so it's 2 out of 9 is not a perfect square. All right. Okay, let's take a look at decimals now. If we look at decimals and you're asked, is this a perfect square? You can use your calculator for a lot of this. So if you do, what does the answer tell you about if this is a perfect square? Well, first things first, remember on your calculator, the square root button looks like this right here, okay? And if you take a number like 6.25 and you take the square root of that number, which I've clipped out here for you to see, the answer is 2.5. So you're saying, well, what does that tell me? If the decimal is terminating, notice this over here, that means it stops like this, 2.5, there's nothing after that. Or if the decimal is a repeating decimal, so it has 1 or more digits that repeat as blocks in the answer, then it's a perfect square. So 6.25 is a perfect square. It's 2.5 squared. But 0.627 is not a perfect square because the answer is not terminating, like this is as many decimal places as my calculator will show, and there's no repeating digits, so it is not a perfect square. Okay, that's how you tell with your calculator. Here's a note on this though. If a decimal has repeating digits or sections of digits, it means that it is rational. It means that it can be written as a fraction, but it does not mean that it's a perfect square. You still have to check. So for example, in here, 0.2 repeating is, if you take the square root, you get this as an answer, and again, that's not a perfect square because the decimal is not terminated and it's not repeating. Over here, 0.44 repeating is a perfect square because look at the decimal. It's 0.6 repeating. Now this 7 over here is just a rounded digit. They round the last digit on the calculator screen, right? So non-perfect square, perfect square. What are these in 0.2 repeating is 2 over 9. And remember, we took a look at this. This is not a perfect square at all. 0.4 repeating is actually 4 over 9. And we know from before that is a perfect square. So that's your connection there with decimals. Okay, what about some more on non-perfect squares? And if you're asked to estimate square root of 7.5, then you're going to use something called benchmarks. You'll hear me or your teacher probably mention benchmarks quite a bit. And those are simply known perfect squares that are near the one you're trying to estimate. So for example, the square root of 7.5. Well, let's take a look at 7.5 on a number line. It's between 7 and 8. And so your benchmarks would be a perfect square that you know that's just under 7.5. Here we go. 4 is a perfect square. The square root of 4 is 2. The other benchmark would be the perfect square that's above 7.5, and the nearest one is 9. The square root is 3. So think with me here. 7.5 is between 4 and 9. So the square root of 7.5 has to be between 2 and 3. Got it? Now, 7.5 is a lot closer to 9 than it is to 4, so your square root is going to be a lot closer to 3 than it is to 2. Okay? So there you go. If you said, something like 2.7 or something like that, that would be a great guess, okay? So there it is on the number line visually, but just think about it. You can take any decimal or any number and pick a perfect square above and a perfect square below, and you know that the square root of that is going to be in between the square root of the ones that you know the square roots of, benchmarks, okay? All right, yeah, you might need to watch a lesson on that if you need to hear more about that. If you use your calculator and you do square root of 7.5, you're going to get an ugly decimal like this one. And if you were asked to estimate, you'd say, well, 2.7 is going to be pretty close. So just 2.7 or 2.74 or whatever, it would be your estimate, okay? Okay, so here's a little practice. If you want to pause the video right now and do A and D, I'm going to show you the answers to A and D in a moment. So feel free to pause the video, give them a try. I've kind of started it for you right here. Give it a try, see if you can do A and D. All right, if you just want to see me do it here now, I am going to show you. So find two decimals that have square roots between 4 and 8, two decimals. So here's 4 and here's 8. Well, 4 is its own benchmark. That square root is 2. The other benchmark beyond 8 would be 9. I know that's 3. So this 8, you might guess would be about 2.9. So if we want two decimals that have that are square roots, okay, between 4 and 8, I have to pick two decimals between 2 and maybe about 2.9, okay? That's it, any two decimals. So 2.1, 2.3, boom. Check them on your calculator, square those numbers, make sure the answers are between 4 and 8. Okay, D, this one's maybe a little bit trickier. I wanted to do a decimal for you, 0.25 and 0.35, okay. Well, 0.25 is its own benchmark, that's 0.5, right? Half of a half is a quarter. And you know 0.36 as well, that is 0.6, okay? That's the square root. And so 0.35 is pretty close to 0.36, so I'm going to say this is let's say about 0.59, right? Let's just estimate that. So I need two decimals between 0.5 and 0.59. So you pick two, it could be 0.53 and 0.55, okay? You double check those on your calculator, boom. All right, so a little bit of a review of the review, okay? Here's, you can take a moment to read this. This is in your textbook as well at the end of the chapter if you have the Math Makes Sense 9 textbook. But a fraction is a perfect square if the square root is a rational number, or if you have a perfect square on top and a perfect square on bottom, you know you're good. As far as decimals, they have to be terminating or repeating on your calculator screen to be a perfect square. Non-perfect squares, as you would be able to tell, they are either not terminating, so they're not terminating and they're not repeating decimals. And the top is not a perfect square and the bottom is not a perfect square. So 143 over 25, 143 is not a perfect square, it's close, but it's not. 25 is, they both have to be perfect squares once they're reduced. Okay, let's move to the second half of the chapter now. 1.3 and 4 talk about surface area. Okay, so again, this is the second half of the chapter, surface area. If you have an object and you're asked to find the surface area is simply the area of the surfaces that would be, and if you think about the real objects, surfaces that would be exposed to the air, okay? So this little collection of cubolinks here, you maybe have used cubolinks in your school career. There's a couple pictures I've got here. So this picture right here shows the inside cube. Now notice that this face here, and then this face on the other side of the middle cube, they are not exposed to the air, so we cannot count those in our surface area, okay? So what we're doing is we're only counting the surfaces of this object that are exposed to the air, and you can maybe imagine that. Now, if you are good at spatial thinking, okay, if you can look at this object and you can kind of visualize it from the top and the bottom and the side, or if you can kind of spin it around in your mind, if that's something that you can kind of do, like on a computer program that would spin something 3D, on the screen. If that's something that it's easy for you, then, this is going to be no problem for you just to think about this like this. This is the way I would do this. If you look at this thing, you would say, okay, let's think about the top is 1, 2, 3, 4 units, 4 square units there. The top and the bottom are identical. So I'm going to go 4 times 2. No problem. That's 8. I'm going to keep that in my little pocket. I've got some more to think about, and I would think about the front face here, 1, 2, 3. So there's 3 there. On the side, 1, 2. On the other side, 3, 4. So we've got 4 more. And then what else? We've got this one there, and one there on the back side. So you've got 3 more. So you've got 8 and 6 and 4 is 18 units. All right, so if you think about it like that, you can kind of spin it around in your head, or you can think about the different directions. Awesome, good for you. They will get a little tougher than this, mind you, so you might want to consider drawing little net diagrams of each face, and that's what this is on the right, okay? So the top looks like this, and you would draw that out, okay? This is what the top, see, look at over here, see, that's what the top looks like. So that's a net diagram. The bottom is going to be the same, so we've drawn 1, 2, 3, 4, 5, 6, 7, 8. The front here would be these 3 on the front, so 1, 2, 3, right? The left side shows 1 and 2, and the right side shows 1 and 2. And then the back side would show the 1, 2, 3. So you can draw net diagrams. If you count those all up, you get 18 units squared as well, okay? So that's composite objects. That's a little spatial thinking. It gets a little bit trickier when you have composite objects. Now, composite objects are basically well, if you think about a composing, okay, so it's an object that's composed of different things all stuck together. In this case, we have a couple cylinders that are glued together. Think about it. Now, remember, surface area is only the surfaces that are exposed to the air. Or think about this as a, well, a cake maybe is a bit misleading, but this looks like a cake to me, like a wedding cake or something. And so this underneath here, I use this word a lot when I teach the overlap area. Okay, your teacher might use a different word, but this is not exposed to the air, is it? Okay, now, so this is kind of like a cake, but you wouldn't, so if you're thinking about a cake, how much would you ice? Like how much icing would you need for the surface of the cake, right? Now this is a bit different because we are going to count the bottom as well, and you wouldn't ice the bottom of a wedding cake. But you can think about it like that, right? You stick 2 pieces together, boom, you don't count the part that's covered up there, right? All right, so here's a little net diagram, and again, I would strongly suggest take a few moments to draw the net diagram. Okay. And so we at the top, here's your top circle, right? That's a top circle. The wraparound part for a cylinder is always just a rectangle, right? 2 pi r is the length, 2 pi times the radius of the circle that it wraps around, times the height. And I won't do this question. I'm just going to show you the net diagram. And so this is the tricky one right here, this surface right here, because it's this big circle, but you have to cut out or subtract the area of this circle that's covering it up. See that? So it's just this part that we want to count, and then behind. So, and then in another wraparound part here, and then another big circle on the bottom. So that would be your net, and I would strongly suggest you just calculating the area of each one of these pieces that you've drawn here, and then adding them all up together. Add. There's your final answer. Boom, done. Make sure you put your units squared, so this would have to be centimeters squared at the end. Okay? Surface area, remember area, squared units. Here's some other examples of some crazier ones, right, that you're going to see from your textbook here, so like from your review or whatever. But again, you got something like this. You could recognize right away this is a cube. Well, what does that mean? Well, all the dimensions are identical. So we have 6 squares like this that are 4 by 4, right? So that could be pretty easy. You could do that right away, calculate that quickly. Then you're going to calculate your surface of this cylinder, the circle up there, the wraparound part. Then you're going to subtract the circle that's covering one of these faces, right? So just kind of piece it together, take your time, double check, make sure you got proper units and stuff. So here we have a triangle. Remember the area of a triangle. Area of a triangle is what? 1/2 base times the height. Okay, base here, height here. So 1/2 that times that. And then this 13 is going to be part of this rectangle, right? That's the kind of this. So just piece it together, and then you've got, looks like a cube there. So, and remember the back sides, okay? So don't forget the back side. Boom, this side. And then the other, there's another triangle, right, on the back side, and then the bottom. So think 3D, right? Think 3D. Okay. All right, so finally here, this is the end here, review of the composite objects. Please make sure that you keep track of all of the surfaces. On a regular prism, there's 6 surfaces on a rectangular prism. Front, back, top, bottom, side, okay, 6. Now, if you have different kinds of prisms, you could have something like a triangular prism, which means that there's a triangle and then there's like a depth to it, okay? It's a prism, and then there's an identical triangle on the other end. Or if it's a cylinder, there's a circle, and then it's pulled apart like this, an identical circle on the other side. That's what a prism is. The two ends, the bases, are identical. Okay. So, anyways, I hope that's good for a review for you. Please make sure you watch the full-length videos. Now, I haven't taught Math 9 for a while. I have not made lesson videos, just making these review videos. So please talk to your teacher, or in the future, look for future videos from Mr. MathWell on Math 9. But there's lots of questions you can ask and lots of help that you can get. So I hope this review has treated you kindly, and good luck on your studying. God bless.